Yeah, Florin, if you want to share your screen again.
Yes.
So hello, everyone. Welcome again to the One World Combinatorics on Words seminar. Our speaker today is Florin Manea from Göttingen University, and he will speak to us about efficiently testing Simon's congruence.
Yeah, thanks very much, Narad, for the introduction. I thought that I will also show you how Göttingen normally looks. This is the one of the main buildings of the university, and it's right in the center of the city. And probably it's called the Alte Mensa, so basically the old cafeteria. And I think that maybe even Gauss and Emmy Noether and these guys used to have their lunch there. So yeah, Göttingen is full of history, not necessarily in theoretical computer science, but mainly in mathematics. And so yeah, enough with this introduction. I just wanted to explain why this building. Yeah, today I will talk about, well, essentially, I didn't change the title on these slides. I built these slides based on a conference talk that one of my PhD students, Mia Koshe, gave a while ago. And it's basically a talk about Simon's congruence and how you can test it algorithmically. But it's more than that. It's about a series of algorithms developed around this Simon's congruence and basically the manipulation of subsequences of words. So in general, a subsequence is a sequence that can be obtained from another sequence by deleting some or zero elements of the original sequence without changing the order of the remaining elements. So that's the Wikipedia definition of subsequences. And you can see that basically if we take this word W, all these words that are written around here are essentially subsequences of it. So for instance, to obtain A, B, A, B, A, you just remove the first B, then this C, then this A, and this D, and this A. You can also obtain it in some other ways, probably, but the idea is that you remove some symbols and you keep the others while preserving their order. Obviously, ABC is not a subsequence because you can get the A, you can get the B like this, but then there's no C that you can obtain. In general, to test whether a word is a subsequence or not, you can just go from left to right and match its letters inside the original word greedily. So that's a very simple way and very efficient way of testing whether a subsequence or a given word is a subsequence of another given word. We won't insist on that, but maybe it's always good to keep this intuition in mind. If we want to find a subsequence, I just go left to right and try to match the symbols greedily. Okay, now based on so subsequences can also be defined in more based on this intuition. So you just call a word W prime a subsequence of length k of a word W if there exist some positions of W where you can read W prime, obviously going from left to right. Now these positions don't have to be consecutive, otherwise we would talk about substrings or factors. And now if you have a word, you can define the set of subsequences of a given length of that word, starting on a, well, not necessarily starting, but contained in a suffix of this word. So subsec KIW is the subset of is the set of subsequences of length k of the prefix starting on position I of W. So basically, if you look at position 1, you get the set of subsequences of length k of the entire word, and that's called subsec k1v, 1w, sorry, and you can have here an example for simple word ABACA. The subsequences of length 2 are those listed in this set. Sorry, I don't know how to work very well with this Acrobat, so sometimes this black thing might appear. All right, so this being said, I think it's clear to everybody what are subsequences. This part where we look at suffixes is important, is a technical detail which is important later in the talk. So don't, get stuck here. It's really just a notation. Now, an important relation for on words defined based on subsequences is the so-called Simon's congruence. It's called Simon's congruence because it was introduced by Imre Simon in his PhD thesis, and it was proven to be a congruence. So generally you take two words, W and W prime, and you say that they are equivalent under Simon's congruence parameterized by a number k. I will just call this sim-k congruence for short, if their sets of subsequences of length k are equal. So W has exactly the same subsequences as W prime when we look at subsequences of length k. And for instance, you have here two words, W and W prime. If you write down their sets of subsequences of length 2, you see that you get exactly the same sets, and therefore we can say that they are sim2 equivalent. So they are equivalent under Simon's congruence parameterized by 2. And if you look at the same words, but consider the sim3 equivalence, you see that BBB is a subsequence of the second word, but it's not a subsequence of the first word, because for instance, here we have two B's. All right, so this means that these two words are not sim3 equivalent. Okay, now a word U of length K distinguishes two given words, W and W prime, with respect to sim K, if U occurs in exactly one of the sets of subsequences of length K of these words respectively. So either in subsec subsec KW or in subsec KW prime. It can be in both of them. We just want to basically distinguish, so to be a witness that these two words are not sim-k equivalent. And in particular, in this case that we see here, BBB is a witness that these two words are not sim3 equivalent. And again, an important notation for us for later, if you have two positions of the words, you just say that they are k equivalent if the suffixes starting on those position in the word W are k equivalent or sim-k equivalent. And we simply say that those positions are equivalent, okay? So I is sim equivalent to J with respect to W, of course, if WIN is sim-k equivalent to WJN. Now, for instance, in the word W, if you consider the suffixes starting on position 2 and 3 respectively, you will get that they have exactly the same subsequences of length 1, meaning that they have exactly the same alphabet. But for instance, W26 contains BB as a subsequence, which is not contained in W36. Therefore, these words are not sim2 equivalent. Okay, so now that we have seen all these settings, there are two important problems that can be defined in relation to this congruence. The first one is, given two words and the number k, decide whether the two words are sim-k equivalent. And the second one is, given two words, find the maximum k for which these two words are equivalent. So on one hand, we have a decision problem, and on the other hand, we have an optimization problem. Sim-k is the decision problem. In maxim-k, it's the related problem where we try to optimize on this k. So essentially find the largest k, which makes these two words sim-k equivalent. Now, because we talk about these problems from an algorithmic point of view, it makes sense to consider or to make some basic assumptions on the model in which we work. And the model is the usual RAM with logarithmic word size. So basically, it's a normal computer where we can store in each memory cell numbers up to n. And also, the alphabet is considered to be an integer alphabet. Maybe that's even more important. So basically, we consider that if we have a word of length n, or basically the largest of the two words in our input has length n, then their letters are between 1 and n. So are integers between 1 and n. Now, this is a basic assumption. It's a usual assumption in stringology. I will not go over and discuss too much about it. If you want to basically read more about why this assumption is not very restrictive, please have a look in our papers that I will mention related to this sim-k equivalence. But if you want, like just some simple salesman advertising, I will just say that this is the assumption under which all the results, all the algorithmic results related to SIMK or max SIMK were developed. Some of them were even developed under even more restrictive or simplifying restrictions. All right, so these are the two problems which we will consider now, SIMK and max SIMK. And the rest of the talk, I will basically talk to you about these two problems and two optimal solutions for them. Now, as I said, this line of research originates in the PhD thesis of Imre Simon, which was done with Janusz Brozowski at Waterloo. I think the thesis was published in '72. And after this thesis, there has been a long history of algorithms and then incremental improvements for exactly these problems or slightly related problems, in which people got closer and closer to optimal solutions for these problems, which are, of course, in linear time. That would be an optimal solution. And what I will what I will show you today is an optimal linear time solution for SIMK. This was obtained in a paper we had at DLT 2020. But basically what we did in that paper was just some data structure like magic to some ideas that Manfred Kufleitner and Lukas Fleischer presented in a paper at MFCS 2018. And basically all this work was caused by this paper by Manfred and Lukas from MFCS, which prompted me to look deeper into this problem and essentially set the base somehow for what we did later. So first, the solution for SIMK. And if you just take this solution and you apply it to max SIMK, you get an on of n log n time solution. I mean, it's clear and it's a rather standard procedure. If you know how to solve the decision problem, then you can do binary search to solve the optimization problem. So it's just some easy observation that from the solution from DLT 2020, you got a solution for max SIMK, which ran in n log n. By the way, there will be a talk at DLT this year given by Pamela Fleischmann on this solution. So today I'm just going to give you some spoilers, and I think Pamela will also cover some other topics from that paper. But for me today, just this is interesting here. So a linear time solution for SIMK. What's funny is that Imre Simon actually claimed at a Words conference, where I think he had an invited talk in 2003, he claimed that basically he presented some tools to work with this congruence, some automata related tools, and he claimed that you can use those tools to obtain a linear time solution for max SIMK, but this solution was never published. And yeah, I tried to use those tools, and I think that the best I could get from using those tools, and definitely not in a direct or trivial way, as Simon suggested, there was something like n log n, so still not pure linear time for integer alphabets, so the setting in which I will present my results. So, after trying to adapt Simon's claim and to adapt this idea from DLT 2020, last year we produced our own algorithm, which is an optimal linear time algorithm for max SIMK. And this is based on a completely new data structure, which is called the Simon tree. And this paper was presented at STAX 2021 earlier this year. If you want to look up, a presentation dedicated to that precise topics, there's also a video on YouTube from STAX 2021. Okay, so I will talk about these two blue topics here. So SIMK in optimal linear time and max SIMK in optimal linear time. All right, so first SIMK, and basically you will see these are based on two completely different ideas, and that's why I wanted to talk about both of them. So in order to solve SIMK, we used a notion which was it's a rather natural notion if you think about it in relation to the SIMK congruence, namely that of a short legs normal form. with respect to the kth Simon congruence. So Simon congruence for a parameter k. So given k, you can define the short-lex normal form of a word as the shortest word u. So if we start with the word w, it's the shortest word u, which is sim k equivalence to w. And if you have more candidates, then you choose the one which is lexicographically smallest with respect to the given order on sigma. So now you look at an ordered alphabet, you can always choose an arbitrary word order on this alphabet if you don't have any. But then the shortest normal form is basically first you optimize on length. So you take the shortest word, which is equivalent to your given word. And then from all the possible candidates of shortest length, which are equivalent to this W, you take the lexicographically smallest one. That's how the short-lex normal form is defined. And obviously this is unique. Therefore, if you want to check if two words are sim-k equivalent, then you can just reduce them to their short-lex normal forms and then simply check if the two normal forms are equal. So that's how you would proceed in this. So that's the big idea that we try to implement efficiently here. And now comes the magic behind this algorithm, which is totally due to Kuffleitner and Fleischer. And they made the following observations. So to compute the shortest normal form of a word with respect to this sim-k equivalence, we will define for each position the x and y coordinates. So the names for these are, I don't know why they call them x and y coordinates. I think it's good because it resembles to the generally geometric intuition that we might have when we talk about coordinates. But basically, you will see that they can be understood very simply. And essentially, x should be read as prefix coordinate and y should be read as suffix coordinate, maybe. So the x coordinate of I, of a position of a word W, is denoted xi, and this is the length of the shortest sequence of indices, I1, I2, IT, so basically corresponds to the smallest t, such that I1 is the position where the letter WI1 occurs in W for the first time. Then IJ is the first position where WIJ occurs in WIJ minus 1 plus 1 I for the first time. And obviously, if A occurs for the first time on position I, then Xi is just, it is 1. So the length of this sequence of indices is 1. Now, intuitively, this means that it's the shortest subsequence. So these indices will give me the shortest subsequence of W, which, if mapped greedily, as I explained, so you match the first letter greedily, then the second letter greedily, and so on, will take you to position I. So in a sense, is a sort of shortest path to get from the beginning of the word to position I, where always, moving from one position to the other is like I go to the next occurrence of some letter. So, first I go to I1 because this is the first occurrence of WI1. Then I go to I2 because this is the first occurrence of WI2 after I1, and so on. And at some point I hit I. And from all possibilities to going or to reaching I in this way, then you take the shortest one. So this is how we define the x coordinate of I. And basically, there is an important property which says that if you have the letter A, and this A is the letter that occurs on WI, and it occurs on some other position, WL before I, such that, everything between L and I is different from A, then Xi, so the shortest sequence of indices that gets me to position I, is the minimum of XL, XL plus Y, and so on, XJ minus 1, everything plus 1. So I have to reach one of these letters and then say, I want to go to the next A. And this will take me directly to XI. Okay, so that's how this X coordinate is defined. Now, this is very intuitive in a sense. I think it's relatively easy to understand what's the intuition behind this X coordinate. Now the Y coordinate is the same, but going from the end of the word towards the front, so moving right to left. The y-coordinate of a position denoted yi is defined symmetrically, is the length of the shortest sequence of indices, such that I1 is the position where the letter I1 occurs for the last time in W, and Ij is the last position where Wij occurs in Wi, Ij minus 1 minus 1. So a similar property to what we have seen before is true in the sense, if you want, the y-coordinate corresponds to the x-coordinate on the reversed word. So you just have to mirror the word, and then the y-coordinate is exactly the x-coordinate. Okay, and as I said, once you have this defined, now Kuffleitner and Fleischer proved two results, or basically it's a big result, which tells you how you can compute the short-legs normal form based on these coordinates. And the first one says, well, first of all, you will compute the x coordinates. And this can be done in a relatively intuitive way. So you don't even have to think about an efficient computation for now. You just can imagine that, you know, it's just like a shortest path type of argument. This is not efficient, but it's clearly running in polynomial time. So you will be able to compute the x coordinates for all positions, and then you compute the y coordinates. But here you do a trick. You get rid of positions from your word whenever the sum of its coordinates is greater than k plus 1. So basically now you go from right to left, you compute the y coordinates, but if at some point you get, you know, to a position where the x coordinate plus the y coordinate of that position is greater than k plus 1, you simply drop that position from your word. And this will also affect the rest of the y coordinates that you will compute. So once you drop the position, this becomes kind of permanent for your word. So you will have to take care when you compute further the y coordinates. But the x coordinates don't change. So the x coordinates are the same ones that you computed first, but then when you look at why, you might drop positions for words from the word according to this rule. And now to compute the short-legs normal form, once you have the x and y coordinates, this is a kind of complicated theorem. If you want to see why all this holds, have a look at the paper by Manfred Kuffleitner and Lukas Fleischer. It's really a nice paper, so I strongly recommend it. It's really good. So to compute the short-legs normal form, now you go again left to right in the word. And if you have two letters, B and A, such that B is greater than A in the lexicographic order, they are interchanged whenever they have the same x and y coordinates, and the sum of these coordinates is k plus 1. So now you go and do some sort of bubble sort. You go through the words, and whenever you see two positions which fulfill this property, then you simply switch them. And you do that over and over again till this situation does not occur anymore. And the theorem of Kuffleitner and Fleischer says that basically that's the short-legs normal form. Now, I think it's a bit, well, you have to think a bit about it, but maybe once you take an example and you work it through by yourself, then you will see that actually this is quite intuitive and it works. And what we have shown in the DLD 2020 paper is that basically this entire procedure can be done in linear time for integer alphabets. And this was no easy job, but basically it also didn't bring any new combinatorial insight. It was just a efficient implementation based on some interval union find data structures, and to do the first part, and radix sort to simulate this sorting in the second part. So I think that what they were doing, their implementation worked in linear time only for constant size alphabets. Otherwise, it was n times the size of sigma. So it was again kind of quadratic. And what we could do, we looked a bit deeper, understood a bit deeper the structure that they are building. and just implemented it faster. So that was the first idea. And now you have seen basically not only that we can check if two words are equivalent, but we can also compute the short lex normal form of a word W with respect to this SIM-K equivalence. So I think this is a nice result per se. So we solve SIM-K in linear time, but we also compute this short lex normal form in linear time, which is a kind of a stronger result. All right, so let's now move to max SIM-K. And this time I will give you a completely new idea, and I will show you a completely new idea how to solve max SIM-K. Now, remember, SIM-K was the decision problem, max SIM-K was the optimization problem. As I said, if you were, if you would have liked to use this idea from here, so computing the short lex normal form, then we should have done some sort of search on K. And this would have led to, in the best case, at least as far as I can imagine, to some sort of binary search. And this would have led to an n log n algorithm for max SIM-K. Now, our idea was to build a structure which is called the Simon tree. And this is based on some equivalence classes which are induced by SIM-K on the suffixes of a word. So just let's split the word suffix-wise into blocks of equivalence classes with respect to SIM-K. That's done in a, that's maybe natural somehow, and it has some good properties. So if you have two positions that are SIM-K equivalent, I and J, then everything that comes between them will be equivalent to them. So because this means that, the word starting on this position and the word starting on this position have the same subsequences of length K. So also the guy in the middle will have the same set of subsequences of length K. What's what's also easy to note is that SIM-K plus 1 is a refinement of SIM-K. So basically, you will just take the classes of SIM-K and split them into smaller classes. And as a notation, position I, or index I, is a K plus 1 splitting position if I and I plus 1 were equivalent SIM-K and are not SIM-K plus 1 equivalent. So so basically, they were with respect to K, and then suddenly they broke up. So it's a splitting position with respect to value K plus 1. Okay, so using these properties, we can build a block structure for a word. And essentially, it's easy to check if two positions are SIM1 equivalent. So I and J will be SIM1 equivalent if the suffix starting on position I and the suffix starting on position J have exactly the same letters or the same alphabet. And this can be checked really easy. You just go from right to left through the word and determine the one splitting position. So you see A is a new letter, then D is a new letter, then A you saw already, B is a new letter, and so on. C is a new letter. And basically you have here the new letters, and these are the splitting positions with respect to 1. So these are your 1 blocks. Now, you can do the same and build the K plus 1 blocks, also going right to left through each block without its last letter. This is a technicality, and this last letter will always form a singleton K plus 1 block. And we determine the K plus 1 splitting positions exactly as for 1 splitting positions, but with respect to that block only, and in particular without its last letter, as I said. So if you go through these blocks, these are the new splitting positions. Maybe here is interesting. When I move my mouse close to the bottom of the page, this black thing appears. So if you look here, basically B is a splitting position because it's alone. Then A is a new letter, and also B is a new letter because, as I wrote here, you always consider the block without its last letter. Okay, so these are the 2 blocks, and in exactly the same way, you can obtain the 3 blocks, and now all of them are singletons. But what's interesting maybe to see is that you see I'm always refining my blocks. So I'm having my 1 blocks, then I'm having my 2 blocks, which were obtained by splitting the 1 blocks, and so on. Now, clearly, if you look at this definition, you would say that this is a quadratic time algorithm for building the Simon tree. And I didn't tell you what the Simon tree is, so let's go there first. But you get the intuition that this is a quadratic time algorithm for building these equivalence classes or the blocks. So to get rid of this quadraticity, I'm going to introduce the notion of Simon tree. And basically this Simon tree is just used to put the block structures in a nice representation. So you have here the 0 block, then the children of this 0 block will be the 1 blocks, then the children of the 1 blocks will be the 2 blocks, obviously corresponding like the way they are split, and so on. And essentially this will, as I said, represent the block structure, and it's used to efficiently partition the positions of a given word with respect to scene K. And very important, the construction takes linear time. So one trick that we will do already from the beginning is that you see once a block becomes a singleton, it stays a singleton. So then I will just don't care about this block on the levels that come after the level when it became a singleton. All right, so how do we define the tree? Well, the root corresponds to the 0 block of W, which is actually the only 0 block. All the entire word or all the suffixes of the word are equivalent as long as we consider subsequences of length 0. And now the children of a block correspond to the blocks obtained by refining that block to the next level. And the nodes corresponding to singletons are leaves. And this tree can be constructed in linear time. As I have said when I presented this talk, so this Simon tree construction last time in this seminar as a short talk, this is very similar to the construction of the Cartesian tree in maybe searching data structures or if you want to call them geometric algorithms. The idea is that we will build the Simon tree right to left as we traverse the word right to left. So basically for each position, we update this tree. And in an update, only the leftmost branch will be edited. And this means that, I will go up on this leftmost branch and detect the position of the current node that I want to insert and simply insert this node while getting rid from this leftmost branch of all the nodes that I have traversed. So it's sort of the same intuition as for the Cartesian tree, but the idea is pretty easy. I just have a tree, I climb up the leftmost branch, and all the nodes that I have climbed will disappear from the leftmost branch in the next iteration, being moved somehow inside the tree. So insert the new position or letter into the tree by moving up the leftmost branch from leaf to root, so moving up. And we find the lowest node that is not split by this position. So basically the lowest node where this position is not creating a new sub-block. And we close all those blocks that we met on the way, and we insert the new position or letter as the leftmost child of this node. We will see an example. So basically that's the tree I want to construct. And this is the tree that I have obtained after traversing right to left the suffix of length 6 of this tree. And now I read this B, and I want to insert this B or to update the tree such that I get the tree for BAA, BADA. So what do? I move up the leftmost branch and basically try to find the lowest node such that, this is the ending position of the block. So I try to find the lowest block, for which this B is not a splitting point. So I look here, is B a splitting point for, the word that starts on position 4 and ends on position 5? Yes, it is. Is it a splitting because it's a B and an A? So basically B is not, by the rule that we have shown, is a different word, a letter from this A. So we just move up. Is it a different, is it splitting this BAA? Again, it's a new letter, so it splits this BAA. So I close this interval or this block, and I'm moving up. Now I have BAAB. Is this B a new node in here? Yes, it is. And basically, when I go up one more, I will see that it will not create a new block. So basically, this interval here is the last one, which is split by this B. I'll just add it as a child here. Now I read the C, and again, so I basically added this node. As you have seen, all the nodes that I looked at, except the last one, have been removed from the leftmost path. So now the leftmost path consists of these two edges. And I do the same for C. It creates a new block. So basically, it's a separate block from this one. And in this node, it will be a separate block. But if you look at it one level up, it will not create a new block. So basically, sorry, it will create a new block because it also closes this block. And now it should be a child of this node. So generally, you just apply this rule iteratively. I think I'm quite bad at illustrating examples, but it's just that you go up the leftmost path and essentially you look at the current node and you say, is it going to split this node? Yes, not. And if yes, then simply go one level up and check, is this node going to be split? And we have this simple rule that tells us whether a node is going to split or not. And basically, you can just apply this over and over again. And this is the tree that you get in the end. Now, there is an intuition why this can be done in linear time. First of all, you'll have to believe me that just checking whether a new letter splits a node or not is simple to check. This is something related to the alphabet. And essentially, when you read a new letter, you just have to know whether the next occurrence of this letter is inside this current block. So basically, the letter that I just added is a new letter with respect to this block or not. And this type of information can be easily computed for our word. So essentially, checking if a letter splits a block or not can be done or can be implemented in constant time. Then, why is it overall linear? Well, because always I'm going through some nodes plus maybe a constant number of extra nodes, like 2 nodes that I have to check. So it's a constant, a long path plus maybe 2 nodes extra. And then I create a new child. And basically all these nodes that I have traversed, except maybe the last 2, are removed from the leftmost path, and they will never be traversed again. Therefore, if you add everything up, you get just linear time, because in your visit, you always visit some nodes, but then you get rid of them. You will never visit them again in this algorithm. So although, inserting a node doesn't take constant time, it all amortizes nicely to constant time. So this is how you construct the Simon tree. So this gives us a nice data structure for a single word, which represents the equivalence classes with respect to SIM-K. That's nice. The only problem is that we have 2 words, and you want to check whether they are, or to compute the largest K for which they are SIM-K equivalent. Okay, so you have a structure for 1 word, but you need to do something for 2 words. And the idea is to build the Simon trees for these 2 words. Basically, they will look like this, and then establish some sort of relation between them. So how do we proceed? We transform the words S and T into Simon trees, as shown already, and then we use the tree structure to connect equivalent nodes of the 2 words. And for this, we will define a so-called S connection, and this is what we will try to compute. Essentially, you have that the node A of the Simon tree for S and the node B of the Simon tree for T, these are our 2 words, S and T, are S connected. And this happens if and only if the suffix starting on position I on S and the suffix starting on position J on T for all positions I of the block A and all positions J of the block B are SIM-K equivalent. So essentially, you pick one suffix that corresponds to node A, and you pick one suffix which corresponds to the node B. And basically, you say that if they have the same subsequences, then your nodes are equivalent. clearly here I say for all positions, but it's obviously enough to check for one of them because all the positions in block A are SIMK equivalent, and the same for block J. All right, this is the S connection, and intuitively what you will need to look out for is the last position in our tree, or the deepest level in our tree, where the nodes that contain position number 1 in both words are equivalent. That's the, that will give us this answer to our max sim problem. But that's hard to compute. So if you want to compute this S connection directly, again, it's not that easy to do it in linear time. So what we will do is look at the larger connection, and this will contain the S connection, and simply refine it. So, this is a larger connection, so it has more connections than we want to, and we will simply go on and cut some of these connections and keep only the correct ones. And this P connection is defined in a very intuitive way. The 0 nodes of TS and TT are connected, so basically the roots. And now for all levels K of TS, if a node on that level A and the node of TS and a node from TT on the same level are P connected, then the ith child of A will be P connected to the ith child of B. So the roots are connected. Then the first node of the first root is connected to the first node of the second root. Second node to second node, third node to third node, fourth to fourth. And maybe if this had 5 children, then maybe this fifth is not connected to anything. And this is the way we can define this P connection. No other nodes are P connected. And very important, this P connection contains the S connection. This is something that can be shown. It's a bit of a combinatorial insight in these trees. So if these are our 2 trees, one for ACAB and one for ACABBA, then you connect the first child of the root, the second child, the first child of the root in TS to the first child of the root in TT, then their first respective children, and so on. Second to second, first child of the second node to the first child of the second node here. The second and third children of this node are not connected to anything because they have no corresponding children on the other side. And same here to these 2 guys, they are connected because they are both third children, and so are their children also connected. So that's the P connection, and now this is easy to compute, okay? So now the only ingredient that we still need is a way to refine this P connection to obtain the S connection. And that's the, maybe key insight in this construction. It's done as follows. We will refine this connection on levels. So first, the roots will always be connected, but then I look at the nodes on level 1 and I destroy some connections. Then I look on level 2 and I destroy some connections depending on what connections I destroyed on level 1, and so on. So I go deeper in these trees and cut connections depending on what I cut on the last level. So how is this done? Well, let K be a level. A and B are K blocks in the word T, respectively S, which are equivalent. And now you take a child of A prime, and a child of B prime. And now I will conclude that A prime and B prime are no longer connected on level K plus 1, if and only if there exists a letter such that the first letter X, the first occurrence X of X after the block A prime, here you have the formal definition of next, but essentially you can imagine like this is, the place where I go from A prime if I read an X. So I read an X and then I start a new suffix in S, and I go to T, I read an X and then I start a new suffix. Basically, these 2 suffixes are no longer equivalent. So, you can already imagine why is this a reason to split A prime and B prime? I am on a position of A prime. Then I read an X, I go to some position in A, and then after this position where X is, there is a subsequence which does not occur in the word t if I go from b prime to the first occurrence of x. So, I start with x, and then in a prime, I will have a word of length k, which distinguishes these suffixes from the respective, the corresponding suffix in t. So that's the intuition. Obviously, it's not necessarily easy to check this in constant time, but it's possible. That's the technical, what's under the trunk in all this construction, which is somehow elegant. The data structures are not that elegant if you want to get this in linear time, but that's the intuition. So for instance, if we look at our P connection for those two words, what we are going to do is, well, first of all, we will look on level 1, and we will first realize that this B and this A are no longer connected. Because for instance, if I look at this block and I say next B, well, next B is the last element of the block. This last letter is also included in the definition of next. It's a technicality. So the next B is in here, while the next B on this side does not exist. So B and the word consisting only on the letter B distinguishes these two blocks. And so I split this. And now I should look at level 1, but there is no reason to split this letter to this block to this block and these two blocks. So now I move to level 2. Now I cut this connection, because if the parents are not connected, the children cannot be connected. I should consider then this connection, and this is also cut because, for instance, I am here, and if I say next B here, it takes me on this position, right? And next B here, it takes me on this position. So basically, I will have to check if the block from here and the block from here are equivalent, and this is not the case, and so on. So basically, I will keep cutting these relations. In this case, all the relations between levels on between nodes on level 2 will be destroyed, and then obviously those on level 3 will also be destroyed. And now I'll just have to look at the maximum level for which position 1 from here is still equivalent to position 1 from here, and this is 1. So these two words are SIM1 equivalent, and you can actually build a distinguishing word based on the way we did these cuts. I didn't really go here very much into details, but you would obtain, for instance, that the word BB is a distinguishing word. Now, as I said, this is the solution to maxim K. Distinguishing word can be obtained, and in order to get this efficiently, again, you would need to use interval union find and interval split find to maintain these blocks, and to also, the union and split part in these data structures is used to maintain this block. The find part of these data structures is related to finding this next X that I'm looking for at all steps. All right, so by implementing this construction of the S connection, we get that maxim K can be solved in linear time, and therefore, confirm that Simon's claim is correct. Maxim K can be solved in linear time. Probably he had a completely different idea, but as I said, I was not able to get to this idea and understand it completely, or understanding it to its full extent. I was not able to use his implementation to get something more than n times log n, if I remember correctly. Okay, some future work. I'm getting closer to the end, or maybe some connected work first. Now, we have seen how you can check if two words are SIM-K equivalent. If they are not, I think it's natural to ask, how far are they from being SIM-K equivalent? So what's the minimum number of edit operations that we need to apply to a word to make it K equivalent to another word? This is an instance of edit distance from a word to a language, where this language is defined as the set of words which are K equivalent to a given word W. So this is a particularly succinct representation for piecewise testable language, as the languages which are defined as all the words which are sim-k equivalent to a word are called. And these are regular languages. And basically, one can see that if you want to define this language using a DFA or an NFA, you might get an exponential blow up, unavoidable exponential blow up with respect to the size of W. So this is a word to language edit distance problem expressed succinctly. What's the distance from U to the language of words equivalent to W? And we have obtained some preliminary results. So a general result we haven't obtained, and I think it's very interesting to understand the complexity of this problem. What we have looked at, a class of languages here. So when you look at these languages, sim-k equivalent to W, we looked at a particular class of languages, namely the so-called K-universal word. So basically, you assume that W contains all possible subsequences of length K. And my question is now, how many edit operations do I need to transform U to such a word? And basically, this is related to the notion of universality of a word. So basically, what's the largest K such that subsec of U contains sigma to power K? So what's the largest K for which U contains all words of length K as subsequences? So we looked at this universality, and we've shown it's actually quite easy that in order to increase the universality, it's enough to use insertions. To decrease the universality, it's enough to use deletions. And if you use substitutions only, then you can obviously both increase and decrease the universality. But it makes sense to look at that case as a particular case of Hamming distance, right? So it's a sort of particular or more particular version of this problem, where instead of using edit operations, you use only substitutions, and instead of having the edit distance, you have the Hamming distance. And in this setting, we obtained some O of n times k algorithms to compute this distance. They are based on dynamic programming, as almost all edit distance algorithms. But if you would just apply directly the ideas that you get from this dynamic programming, you would get something like nk square. Then if you use some, already smart optimization data structure, or some nice data structures to optimize this, you get first n times k log k. And we really had to work a lot to get n times k. So we built some particular data structures, although admittedly, this doesn't bring any combinatorial insight in the problem. It's just some sort of, nice implementation and nice algorithm. What's also interesting is that if you only consider increasing the universality, then you can get something like n polylog sigma. And this is, again, you hit the problem with some very heavy data structure machinery. Basically, you prove that computing this distance is equivalent to computing a minimum weight k-link path in a directed acyclic graph, which fulfills the concave-Monge property. So it has some nice algebraic properties. And what's interesting about these two algorithms, on the one hand, if k is constant, then you get a linear time algorithm. On the other hand, if sigma is constant, then you get a linear time algorithm. It would be interesting to prove some lower bounds on these problems. And this is where we stopped in investigating this. I think it's an exciting problem, so I would recommend that you look at it. Another connected work is to look at absent subsequences in words. So absent substrings is really a hot and nice and important topic in stringology. I saw earlier that Gabriele was here, so he has some wonderful works on absent substrings. And also at CPM this year, there's a nice paper on absent factors by Solon Pieces and others. So this is a nice topic in stringology. Oh, I think it's natural to ask about absent subsequences. And we played a bit with that. Obviously, you can have two types of nice absent subsequences: the minimal absent subsequences, which are those absent subsequences whose every subsequence is not absent. And then you have the shortest absent subsequences, which are absent subsequences of minimal length. And you can already have the intuition that these shortest steps and subsequences are very well connected to the notion of universality. So basically, the length of these shortest steps and subsequence is 1 plus the value of the universality. Now, what we obtained, we obtained some precise combinatorial characterization of the set of minimal absent subsequences and another characterization for the shortest absent subsequences, which occur in a word. We have words which have an exponential number with respect to the length of W of minimal absent subsequences and also of shortest absent subsequences, respectively. And what we have also done from a combinatorics on words point of view, we know which is, or one of the words which has a maximum number of shortest absent subsequences among all k universal words. From an algorithmic point of view, we can compute efficiently minimal shortest absent subsequences, minimal or shortest absent subsequences, and we can also compute representations of all these subsequences, which allow us, I don't know, to search efficiently for these subsequences. All right, and this is all I wanted to tell you. I will end with thanking my co-authors. So Joel, Pamela, Mia, Tore, and Stefan were co-authors on the paper related to edit distance, which also appeared at Stacks this year. Pavel, Mia, Tore, and Stefan are co-authors on the paper about the Simon trees. And Mia, Tore, and Stefan are co-authors on the paper related to minimal subsequences. So thank you all. Thanks to my co-authors for helping me getting these results, and thank you all for your attention.
Thanks, Florin. Does anyone have any questions?
I have a question.
Yeah, go ahead.
Thank you for the talk, Florin. If I remember correctly, it was in Salerno, no, where the Imre Simon presented his remarks, or
it was Words 2003. I was not there, so I was just barely finishing my studies at that point.
Oh, I see. So I wanted to ask whether his remarks are somewhere fixed, or
so
like
there is. So I found on.
Or...
So on the internet, you know, it's the internet that knows everything. So there is this paper which contains the I think extended abstract of his talk there from Words, and basically he presents there an approach to solving these problems based on automata. I can dig it up and send it to you by email. So I don't think that there is any formal proceedings, and there I think he claims that these results can be adapted to solve MaxSim. Now, I have to check the list of participants, if I may. I think, I don't know if Maxim is here today, but at some point, I think I also asked him about this, and he also did not remember whether, or not he didn't remember, he didn't know whether actually Simon really had a proof for this or not. So unfortunately it was lost to, because, you know, Simon passed away.
Yes.
More than 10 years ago, unfortunately, and it was never clear whether he had a solution or not. So that was never published. I really dug this up before the Stacks deadline, before submitting this paper. I didn't want to make a claim that was unchecked. I couldn't find anything. Also, when hearing our talk from Stacks, Volker Dickert said that probably Imre had a solution. So I should, you know, always assume that he had a solution, but simply it was not written. What we did was just confirming this claim. So I don't know about his solution. I know his approach. I tried to make it work. Didn't happen. But that's my fault.
And there is any record of your attempts in this direction, or?
No, I mean, I didn't write them down. So generally, it's basically trying to implement efficiently that this automata that he was building there. And well, I mean, if you try to implement automata, an automata that has n states over an alphabet with sigma letters, then you always would have some problems, given that, you need to have some sort of efficient implementation of the mapping. And either you will need, log sigma time for each to make a move, or you need something like n times something depending on sigma to store the automaton so that you make these moves efficiently. So if you work under this assumption that the alphabet is integer, then basically you might end up in something like n log n overall. So that's the intuition. Now, I didn't take records of my, failed attempts to make something work. Probably it's a lot of dumb stuff there too. So
Thank you.
thanks for the question.
Any other questions? If not, thank you again, Florin, for your talk.
Thank you.